Having discussed Fermat's little theorem, we are going to look at some applications of Fermat's little theorem next. So first thing is we just want to make sure we have a good understanding of what Fermat's little theorem does. So if I look at this, if we know that 243 is prime, we want to determine the value of the expression below, okay, and we want to justify our answer. Now, I'm going to do a verbal justification. You would normally have to do a written justification, right, because you're turning this in on your homework, okay, so make sure to do that. In any case, we know that, so since 243 is prime, right, okay, and we know that 743 does not divide 2, right, okay, so I'm thinking Fermat's little theorem, okay, and so then we also notice that 743 minus 1 is 742. Okay, so this is fitting the assumptions of Fermat's little theorem. And then, so according to Fermat's little theorem, since P does not divide A, and this exponent is P minus 1, right? Okay, so this is P minus 1, this is A, and then this is P, so then this should be congruent to 1, mod 743. Okay, and if you're kind of unsure, feel free to go to Wolfram Alpha and check. Okay, or maybe you want to use the fast powering algorithm or something like that. Okay. Next application of Fermat's little theorem is to look at multiplicative inverses. Okay, well, according to Fermat's little theorem, again, if we meet the certain set of criteria, we know that a to the p minus 1 is equal to 1, right? Or congruent to 1 mod p. Okay, and so then what I can do is multiply both sides by a to the negative 1. So this is a to the negative 1, and then this is a to the p minus 1, and then this is congruent to a negative 1. Okay, mod p. And so then at the end of the day, what I get is a to the p minus 2 is congruent to the inverse of a mod p. Okay, so then that's kind of what we want to move forward with. So now we have the extended Euclidean algorithm to find multiplicative inverses. We also have Fermat's little theorem, which is faster. Okay, so let's just double check this. Let's find 29 inverse mod 257. Again, you can check by extended Euclidean algorithm. Or if we think about this, this should be, okay, so this is, again, I'm just thinking, okay, so this is A, this is P, so then what I should be able to do is say that this is 29 to the, okay, P minus 2 is 255, and then I want to look at this mod 257, okay, and then fast powering algorithm, or Wolfram Alpha, you end up getting 195. So this is congruent to 195 mod 257. And just to double check, okay, so that should be your answer. Just to double check, you can do 29 times 95 and then do this mod 257. And when I did it, I indeed got 1. Okay? So make sure to double check that on your own. Okay. The last application, and perhaps the most useful for us in number theory and cryptology, is thinking about if Fermat's little theorem can help us detect primes. And so what I want you to do here is to think about the contrapositive of this statement, because again, truth values are the same. So see if you can write down what the contrapositive would be, and then resume the video. Okay, well, here's how I think of the contrapositive. Well, if we know, generally speaking, that if we have a to the p minus 1 is congruent to 1 if p does not divide a, okay, so that's the general statement. Then what if we say, well, what if we do if a to the, this is sort of the then part, okay, if p minus 1 is not congruent to 1, then, and then this is also, that's a condition on this, but then this is also the conclusion for the contrapositive. Okay, so I'll just make this clear, contrapositive. Okay, so here if this is not congruent to 1, then P is not prime. Okay, so this could help us detect primes. Let's see if it does work. Okay, so we want to determine if this is prime. Now, I've done some Googling, and this does, and you're welcome to do Googling too for this exercise. This ends up being a prime number. So what I want to do is pick a number A, and if this is prime, I want to use an exponent on it, and then see if I get something that's congruent to 1. So what I'm going to do is I'm going to pick a random number, my favorite number, 7. Okay, I'm going to do 7 to the, and then this is my prime that I'm testing, so 655, 37, and I want to know if this is congruent to 1 mod, oops, this should be p minus 1, this is 65536, okay, mod 65537. Okay, and so here I would go to Wolfram Alpha and type this in. Okay, feel free to do that on your own, and I do indeed get that it is equal to 1. Now this is sort of using the Fermat theorem in kind of a haphazard manner, because I'm testing if it is prime or not, but I'm not really using either the direct statement nor the contrapositive. I'm kind of doing this hybrid. Eventually what I would do is I would do this little check, see if I get congruence to 1. If it does, then I can use Fermat's little theorem in the normal version and not the contrapositive, and I would just say, okay, well, I have my prime, I have a number, and it's congruent to 1, so I'm good. If I am testing, if I don't get this condition, then I'm sort of I'm like thinking the contrapositive, but and I would end up saying like P is generally not prime if this doesn't work out. Or maybe this is just a place to start the discussion of, okay, well, we didn't get that it's congruent to 1, so then we don't think it's prime, and we just want to maybe confirm with another method. And so this is just meant to be an overview or maybe a stepping stone as far as primality testing.